Test 1, 2, 3. Sound check. All right. Bit of a technical difficulties, but I'm here. And so is the music. Any second. Oh, I'm about to be live. Oh no. Okay. Alright, hello. Just running a little late, like usual. Let's see. Okay, so time to post my spiel. So today is gonna be a bit of a special one, because it's by request. And it's gonna be on logarithms. Yay! So I'm gonna be live for about an hour. If anyone needs help. There it is. Alright. So, logs. Okay, so today is going to be a continuation on last week, which was about... And this time it's going to be about logs, which is like the other half that kind of goes with it pretty well, I think. Now, once again, I need to give credit where credit is due. Because this guy that I found, he's so smart, he's so cool. And I really want to give him a shout out and give him credits as I go over the subject matter. And it is Malev, the Diabolic Vtutor. Yeah. So let me just try to get a screenshot there, so that can be like as a reference, as well as a link this time. I don't know if I sent one last time, but he does good stuff. Okay. Let's see. How do I not do the timestamp? Share? Copy. Okay. And then, sorry if it's just trying to get my things together. I don't know why it has that extra stuff with the question mark. Is that like tracking info? I don't want to do that. That should work. That link should work if anyone wants to check it out. So here's a guy that was able to kind of cover on his stream about log functions, how they work, and I was able to squeeze it in about 2 hours. So, you know, a little nice and concise covering about it. Let's see if I could find a good timestamp, actually. There should be... Ooh, I like that one. When was that? So I'm going to use his material that he provided as reference. And thankfully on his video, if you ever want to go over logarithmic functions as well, he provides the timestamps as well as a comment. So very professional stuff. I like it. Ooh, oh, this is a great screenshot. I just gotta line it up. Pardon me, I'm not totally prepared. There it is. Okay. Bam. Alright, there it is. And of course, using what he has provided here, which is I was going to use for my material, but instead of writing it out, thankfully I can just kind of draw on the picture of the stuff that he has provided to kind of explain logs. Now, for exponents, just to kind of review for a little bit, it's basically where you have a number like 2 to the power of 3, and that can also equal 2 times 2 times 2. These combine to be 4, and then that times 2 becomes 8. That's your answer, right? And with exponents, there are like some weird special rules that you could do. And log functions is basically kind of taking those rules as well, but being able to better solve the issue of what if you have a variable in the exponent. So say, for example, if you have something like, let's try it like this. 2x equals 8. Now, of course, using context clues, we could probably figure out what the answer is. But pretend as if we didn't, right? We didn't exactly know how to solve this. And now, of course, you could just kind of brute force it, which is to say, okay, well, 8 breaks up into 2 times 2 times 2, and then that kind of equals 2 to the 3, and then you have 2x equals 2 to the 3, and then, you know, if you just kind of take out the bucket of stuff that's holding it, then you could just have x equals 3. Now again, this isn't quite logs yet, but this is some kind of principles that we will be using for logs in a bit. But basically what this kind of, the way that I jumped from here to here is because when you have a large number and it can kind of break down into smaller numbers, especially numbers that repeat itself, then you can make it into an exponent formula. Just like how, you know, you can kind of go from here to equal this, you can do it backwards as well. So then that way you kind of have this nice matching thing where they both have the same base value. Similarly, if you have some kind of like crazy funky formula, like, oh, what would be weird? I don't know. Let's make up some stuff, right? Let's say x plus y to the power of z divided by 84 well, that's not 84. Equals x plus 1 to the power of z equals 84, right? Maybe you have some kind of weird, funky equation like that, and you could kind of course, go through each step to cancel these things out. But, I mean, if you just kind of eyeball it, and you're trying to solve for what is y, then you realize that a lot of this stuff around it, it just kind of distracts from what it is, and you can just kind of pull it out and look at the 1 here and the y here, because you got 84s on both sides, you got to the power z on both sides, you got plus x to both sides, and then you're just kind of left with y equals 1. Now that's kind of a more silly example of it, but in the same way, there's this principle where, you know, if it looks like one thing and they kind of equal each other, then it's probably just that thing. Of course, there's an exception to that rule, where, say for example, if you have 25, no, hold on, 5 to the power of 2 equals x to the power of 2, right? And so you might say, use the same logic and say, oh, well, that's easy. If it's this, then I could just kind of get rid of these things, or do the square root on both sides, and then you're left with 5 equals x. Yes and no, because you have a squared number, then actually it could be either x could equal 5 or it could equal -5. And if this was a more complex problem, then, you know, of course you'd plug it in and see what works. But even with the simple problem of, you know, 5 squared equals what, -5 squared, you'd still say that they both equal 25, and they would both work, so then your answer would be both. So that's a little bit of funkiness there. But generally, if you kind of eyeball something within a large, overly complicated nested equation, and if they're just kind of in the same spot and everything else is equal on both sides, then yeah, probably you have your answer right there. You don't need to really reduce it. But of course, it's important to do so as part of your work. And so doing that part of work is using logarithms. Because just like how we're kind of covering, well, what if you have a positive exponent? What if you have a negative exponent? What if you have something weird where the exponents, like, you know, multiply? Or what if you have an exponent that divides, right? Just weird stuff like that. Now, of course, this is all assuming that we're trying to solve for some kind of variable that is not the exponent itself. And what logarithms do is that they kind of let you solve the question of, well, what if it's something funky like 2 to the power of x, and that equals 4. Well, how do we solve that? That's a good question. Again, we could try to do the brute force method and just break it apart, and that will be an important skill for later. But for now, we're just going to practice using logs as kind of a way to break that up. So, for example here, we have this nice little equation, log b a equals c equals bca. That's a bit obtuse, because you're just using variables and you're kind of shuffling them around. But a nice kind of visual way to kind of imagine how this works is when you're going from, and I'm going to try to do it the nice easy way first, and then the backwards way, in which we'll actually apply to right here. If you have a log smiley face, right? And you're trying to figure out something, but then you have like a hat. Again, silly, I know. But the way you actually have this thing is that you could pretend these are each variables, right? They're just as good. And so then what you would do is you just kind of scoot the smiley face underneath the hat to solve for the question mark. And then you kind of have smiley face to the power of a hat equal your answer. Similarly, if you have something like this, where you're trying to solve for, what's the hat, you can work backwards and then basically do the log of the question mark. And again, it seems a little weird, but then you solve for the hat. Again, silly, but let's just try it out, right? Here we have, not smiley face, but we have 2 to x equals 4. And using the more sensible equation that we have here, we would actually put the log function of the exponent. Oh, wait. Sorry, misspoke there. We would carry the exponent to be its own thing. And then we would have log, let's see, b2 to 4. Alright, so we got that, right? And maybe this could be your answer. Maybe you could say, okay, well then I solve for x. It's this weird thing, log 2 base 2 to 4. However, now we could also still apply that principle where we can break things apart. And 4 can also be known as, let me just draw it on here, I guess. 4 equals 2 to the power of 2. So then you have this weird thing now where you have log 2 to the power of 2 equal x. And so now it kind of seems a little weird, like now we're just shuffling numbers and I still can't quite figure out what we're doing. But then we would go to, I believe, yeah, these two equations down here. Well, I think there's one missing. Yeah. Okay. The one that we're missing is a principle that I should probably have explained before. But we'll get to that in a bit. Another rule is that if you have a log function and it's to an exponent or to a power of something, then you could drag that to the front. Now, this can apply to a lot of weird things. Like if you have a log b a to the c and it's c plus 1 and that is the whole exponent, then you would drag to the front c plus 1 times log ba, but I don't want to overcomplicate it right now. But that's just to kind of show that it's a pretty flexible thing where it takes the exponent chunk right here. Actually, maybe I shouldn't have done it like that. Probably would be better like this. There you go. Alright, so now what we could do is we could drag out the 2, and then now we have 2 log. Oh, my head. Sorry about that. 2 equal x. Now here we have this kind of weird thing where you have log 2. Is there anything special about that? Well, actually, yes, there is. Because if we kind of go back to our principle of these things, where we would, let's say, let's take a different number, right? So it's more confusing. Let's take log 7 equals, we don't know, right? Well, now what we would do is we would drag this kind of underneath and figure out, okay, just like how we put the smiley face into the hat, we would have 7x equal 7. Now, why would we do this? I thought we were trying to actually solve for exponents. Why would we go backward like this? Well, the reason why is to show that when it comes to this very unique thing, and I believe this only works for numbers that are greater than 0, but if you have a log with a base number to the same base number, what ends up happening is you get this kind of weird funky thing where it's the number equals a number. And last time I kind of covered just like how if you have a variable, it kind of has an invisible 1. They also have an invisible exponent to the power of 1. So then this would actually be 7x equals 7 to the power of 1. And because, again, we could kind of just ignore the chaff around this thing, we could just simplify it to x equals 1. So part of actually doing logs in your work is it's very, very lucky and very nice to see something like this where you just have part of your equation look like this, where it is a log with a base number that matches the number within the log itself, because this whole thing just becomes 1. And because it's still being multiplied to the 2, then your answer is 2 times 1 equals x. And then that ends up, of course, being 2 equals x. Alright. Now, again, that could have been very obvious looking at it. If we just were to start from here and say, oh yeah, it's probably just 2. If we just break it apart, 2 to the power of 2 is 4. However, the practice of kind of going through these steps in your math assignment, even if it seems very obvious, is important because it shows that you're able to kind of master how to use these functions and these equations, how to break it apart properly, because it gets a lot messier. And when it gets really messy and you think, oh, this is a horrible problem, I don't know what I'm doing, then just kind of going back to the basics like this, just working through it and going through the principles that you know will then clear things up and make it a lot less confusing. Now, as for specific examples that we can go over, please wait a bit while I try to figure out where that is in these textbooks that I got. So pardon me a little bit. I just gotta do some Control F searching. But meanwhile, let me zoom out a bit. This is kind of the core of the class. It's just kind of applying principles like these over and over again. Oh, F log? Will that work? Logic? Nope. I think these are all linear equations. Oh, I forgot to go over the quadratic formula. Okay, well, something that might happen later on, and I might have to go backwards to kind of cover this, is maybe the quadratic formula. Because sometimes I would apply to this level of math, where you might get some weirdness, where you would have an equation where it's like, oh, I don't know, x squared plus x minus 4 equals 0. You would get something like this sometimes, because when you end up reducing everything, and you go through some of these principles, you might end up like that, especially with this one, where if you have two logs that can add to each other, then they're actually being multiplied to each other. Say, for example, if you have, let's see, log 10x plus log 10 3 plus x equals 0, right? It's a random thing, right? And just like how with exponents, where you can kind of multiply them together, even though it looks like they're adding, here, I'm kind of poorly explaining it as a moment, because I haven't gotten into depth with a proper equation quite yet. However, I just want to show that it can get a little ugly, because the way that you would reduce this thing is to actually shorten it to something like this. Log 10 3x plus x squared. Wait a minute, I'm missing something. Yeah, sorry, I'm just trying to write out a formula. Alright, equals 0. That's probably wrong. Anyways, you can end up with accidentally having the quadratic formula and needing to use it at some point. when you go over logs. Sorry, while I still try to find a proper example. Just need a little bit more. Aha! Okay, here we go. So, now also you might be wondering, well, why do you have to do this, right? Aside from just, of course, having the class and needing to listen to the teacher and sort things out. You know, I find that when kind of reviewing this logarithmic functions and all these things, they kind of just give you the functions and you just kind of have to solve and apply it repeatedly to a bunch of math questions. I think it's mostly almost like a puzzle solving skill. Rather than like, you know, you absolutely need to know this for life. It's more like, how can you apply the logic of how a system works and then break it down from a very complex situation and use these rules that you have to break it down into pieces, and even if they're nested in each other, how to constantly apply it until you can reduce it to something that can make sense. So let's say, for example, if you have like a more complex equation, how can you use a bunch of rules and processes and things like that so you can break it down to have a very simple solution to find out what is the problem in which you're trying to solve. Here it's math and it's numbers and you're trying to figure that out, but I find that that can also be applied if you have other rules in life, and you just need to follow those rules and apply them even if they're nested in those kind of situations to figure out how to navigate things in a way that you would find good for yourself. So that's the purpose, I think. Or maybe they just want to waste your time with logs. I don't know. Let's see if I could find one. Oh, I can, but they kind of have the answer with it. Okay. Yeah, sure. This is kind of simple. Now, again, that's not to say that if you're someone that's working on this and you're struggling with it, hopefully these examples I will provide will seem simple, and then you can kind of apply it to yourself. Alright. So, for something like this, where you have kind of in the reverse. Now, just because you have these rules, they equal to each other, they can also go back and forth, right? It's not just kind of left to right where you have plus, it only goes into multiply. If you have things that are multiplied, you can break them apart to where they're plussed. Similarly here, if they're divided, they kind of minus each other. Now there is a way to explain this can relate better to exponents and how the rules of exponents apply to these directly. However, when it comes to practically doing logs, I find it better to just kind of memorize these equations, just like how you would memorize the rules for exponents. They're just kind of the same thing, but slightly tweaked. So here in this example, and again, they have the answers here. They have this equation, which would be basically log, let's do a b times c, and they break it apart into log a, b, plus log a, c. And here they do that splendidly, where they retain the same value of the log and just break the numbers apart. Now what do they do here? Oh, that's it. What? That's it? They just stretched it out? That's the whole thing? Well, I mean, you know, I guess is the part where they just kind of explain the rules. I thought they're gonna try to solve for x. Can we solve for x? Hold on. Not really. I mean, kind of. Let me think. Would I should be able to apply that equal A? Yeah, kind of. Alright. Let's do it like this. So they gave something weird, which is log 3 7x, and they just kind of stretched it out. But we could actually kind of change it a little bit by making it equal 3, because we're using this rule right up here. This is going to be kind of our bread and butter. Let's see. No, wait. Darn it. We put on the hat, it's x, and then that equals what, 7? Yeah. I have to figure out, okay, what number, 3 to the power of what equals 7? Well, that just made things worse, doesn't it? Actually, wait a minute. Could I have solved it by splitting it apart? Okay. Pardon me while I try to figure this out. I'm trying to do math wrong. Let's see. 3 times 2 is 9. And then 3 times 1 equals 3. So it'd probably be like 3 times 1 point something equals 7. Yeah. And so when you have x kind of equals that 1 point something, and it's just kind of a weird number, then there's probably some weird way in which we could have probably done the quadratic formula and squeezed it in there to figure this out. But, again, do what your teacher wants, right? If they just say, hey, stretch it out, show the property, then that's your answer. But let's see if I could find a proper one. Woohoo. Oh, this one looks gross. I like it. Which one do I want? Okay. Let's try this one. So we're going to work on the second one. And do the same property. Again, follow the rules first, right? Write each logarithm as a sum of logarithms, and we're going to simplify it. So the answer isn't going to be that we're going to necessarily solve for x or y, we're just simplifying. So, now what might seem a little weird is that now you have not just one thing, 2 things being multiplied, now you have 3 things, right? How do we break it apart? Because normally in our sample we only have kind of a and c being multiplied to break it into a plus c, right? All the nice thing is that the rule just kind of applies, and you could do it multiple times. I mean, just eyeballing it, I kind of know how it works, but to kind of go through it and explain. If we have log 327xy, right? That would break into, and let's just try to separate the variables from the number. So that would be 27 plus log 3xy, right? But we could just do it again, because this is kind of like nested within that, or we could just reduce this even further. And so we could carry down the, and sorry for my poor penmanship, log 27 plus, so this is all the same, but then this one also gets split up too. Log 3 x plus log 3 y. Now, It looks done, right? Looks pretty good. However, we could probably do a little bit more. Because if we go back to our rules, we could break this thing up into little numbers. I know there's a technical term for it. I forgot what it is. But 27 also equals 3 times 9, and then 9 also equals 3 times 3. So 27 is 3 times 3 times 3, which is also known as 3 to the power of 3. So then we get this weird thing where, you know, maybe you would think that this side is basically done. Because it has numbers, we can still kind of monkey with it and make it even simpler. Alright, here we go. So then we have log 3 to the power of 3. Well, look at this. Oh, this looks like a, whatchamacallit, like some kind of jackpot. But no, it's just math. Alright. So using, again, one of our previous rules, where we can get the exponent of a number and throw it to the front and multiply the whole thing by it. We could throw the 3 in front and get 3 log 3, 3. And just kind of like in my previous example of, where was it? Oh no, did I lose it? No, I didn't erase it, did I? Oh, it's right here. No, that's not it. Where is it? Anyways, if you have something that is to the log of the same number, that basically this whole brick equals 1. So that's a neat little shortcut. So then you have 3 times 1, which also equals 3. So then this whole equation actually equals not log 327, but 3 plus log 3x plus log 3y. Okay. Is that the solution? I guess so. I don't know, I feel like I could probably monkey with this a bit more. Let me go back to what we originally had. Okay, so we have this, but these aren't multiplied to the power of 3. Okay. Then it might need to split like that. Log 3xy. Oh! Aha! Okay, I see. No, because there's no equals. Ah, shoot. Alright, I was getting a little ahead of myself. To explain what I was thinking, well, what if we have log 3, 3, whoops, well, 3, plus log 3 xy. And could we have maybe gotten rid of the log 3's to just have something like 3 equals xy? However, that doesn't quite work because there is no equal sign for us to work with. There is no equals in this equation. We only have these things being added. And so because we have these things being added, we don't want to further reduce it using where we do from one side to another because we actually don't have the other side. We don't have an equals equation. So you can't be doing some weird stuff where we multiply everything by 1. I mean, you kind of can, but you can't be doing like big reductions where you can kind of, you know, cancel out things from one side and cancel it out from the other side because, again, there's only one side that we're working with. So this would be wrong if you try to go that route. You kind of just want to go the long route. And then maybe do a little bit extra where you end up with 3 instead of something like log 327. Alright, cool. Now let's see what else I can grab. I like this one. Okay. And just to kind of show off on the opposite side, right? And I'm going to do something wrong in the meanwhile. Because, of course, you know, you don't... If you want a proper good lecture, on how to do things right, you can listen to the classroom, right? But if you want to learn how to do things wrong and how not to do it, you know, you can come here. So, if you have something like log, let's say 3, and then instead of being multiplied, what if it was 27 plus xy, right? If you have something like that, oh, well, that's a little messy. Hold on, let me clean this up. Plus x, y. There we go. That's still too small. Okay. Could you have done the same process? The answer is no, because what you have here is a plus. And just like when you have weird stuff with exponents, where let's say, I mean, if you have, what was it, 2 to the power of 2 times 2 to the power of 4, then that would be 2 to the power of 2 plus 4, right? Which would equal 2 to the power 6. And then that's an actual number, right? But if you have something funky where it's like 2 to the power of 2 plus 2 to the power of 4, yes, you could solve that as a number equation, but you cannot combine them. And in fact, I think it becomes easier if I just don't use 2, and I use something like a variable. Ooh, yeah, let's try that. Let's try g. Nope, that's confusing. Oh well, we're doing it. Alright, so g to the power of 6. So if you have g to the power of 2 times g to the power of 4, then you got g to the power of 2 plus 4, that equals g to the power of 6, right? And then, you know, that way we don't get confused by trying to solve the equation. But if you have something like g to the power of 2 and g to the power of 4, if they're added to each other and they're not multiplied, you cannot do this little bit where you add up the exponents. This would have to be a separate process, where they're just kind of apart. This just might just be your answer. It's just kind of stuck there. And yeah, you could do some, like, I guess funky stuff, like g to the power of 2 plus g to the power of 2 plus 2, and then I guess that would equal like g to the power of 2 plus g to the 2 times g to the 2. Yeah, that's a terrible looking g, I'm sorry. But again, like, this doesn't really change much. Your answer just might be here because you're stuck because that plus and that minus in the wrong spot kind of messes things up. Similarly, when it becomes logarithms, if you have a addition or minus symbol in the thing in the middle, right here, then a lot of these rules and principles don't really apply to kind of break them apart or to minus them as log functions. Instead, you would consider this whole thing as one variable. So instead of thinking of it like, okay, here's 27 plus x and y, you would consider this whole chunk inside as like an x. It's treated like a whole variable because it cannot be properly split using logarithmic functions. Now, maybe using something else it might work, right? If it was like log 3 x squared plus x plus 1, then yeah, you could do the quadratic formula and like simplify it and do those kind of shenanigans, right? But for the sake of logarithms, if you just have this whole thing, that's still like considered one big chunk. So don't try to mess with that. And well, don't try to mess with it in terms of these rules that you'll be applying for. Okay. That being said, right? We're not going to have this issue for this equation because now we're going to try to do the flip side of it a little bit with dividing. Because normally we've been doing what if these numbers are multiplied together. Oh my goodness, I only have 10 minutes left? No! Ah, okay. Alright. If they're divided, then what can you do, right? You could still split them up, but instead of being added, they're minusing each other. And just like how if you have an exponent and it's I don't know, q to the negative 2, that also equals 1 over q2, right? It gets flipped. With logarithms, visually kind of the same, where if you have something being divided, well, I guess I'll just look over the rule over here. If you have something that's being divided, then they actually become minusing each other as logarithmic functions, but you would keep the same base. So here in this example, they split up the 5 and the 7 to be this equation, and using the, I forgot what it's called, but basically these things cancel out and become 1. And there you go. Now, what if it was something weirder, right? What if it was something like, what's a good number? No. Nothing really begins with 7. Okay. What if this was 25? Oh, wait. Yeah, no, you could probably solve that. Alright, what if it was 25, but you couldn't just, you know, do the whole fraction thing and make it like 1 over 5? What if you had... Actually, what if you did, right? Okay. Let's do this wrong. I like it. Alright, then you got log 5, 1 over 5, because then, you know, you cross these out and then it becomes 1 and then 5. Oh, the reason why that works is, again, sorry, I can't really be jumping ahead like that. Let's see. 5, like that. 5 over 25. No, it'd be like this. Sorry. 25 equals 5 times 5, and then you have a 5 here. And you could cancel these out, then it becomes the 1, and then there's the 5. So that's how we got log 5, 1 over 5. Assuming that we changed the bottom number 7 to 25. Now that we did that, we could also make it so that this still would apply to this principle. So then we could do something funky like, let's say, log 5, 1 minus log 5, 5. And then this whole brick turns into 1. We keep the minus. And then log 5, 1. I think that's an answer to something. Hold on. If we apply the same principle, log 5, 1 equals x, and we're trying to solve for x, what would this be turned into? Then, of course, we put underneath it 5 to the power of x equals 1. Yeah, I don't think that works out. Darn. Shoot. Yeah, because it'd be like 5 to the power of 1 equals 5. No, wait. 5 to the power of 1 equals 5. Oh! Wait a minute, it does work out. I forgot. Anything to the power of 0 equals 1. So then, hold on. 5 to the power of x equals 1. But if x equals 0, then it'd be 5 to the power of 0, which would equal 1, which would work. Ah, I knew it. I knew I smelled something in there. Okay. And again, to figure out why 5 to the power of 0 equals 1, that would be on last week's lesson on exponents, on how that equation works. So then, for our silly example, right, then we could say this log 5 to the 1 would actually equal 0. So you have 0 minus 1, and then your answer is negative 1. Does that make sense? But then I think that would mean that anything that is log base value, with the inner number just being 1, would have to equal 0 all the time, right? Is that true? Hold on. let me double check this guy. I think he mentioned something like that, but I forgot. Let's see. Whoopsie daisy. How do I do this? Oh my god, I was right. Holy crap. Yeah, okay, I just rediscovered something that was already explained a long time ago. But yeah, an addendum to this thing is that basically, log... Oh no, wait. Maybe I did it wrong. Hold on. Log b to b equals 1, so long as b is greater than 1, or 0. Okay. That makes sense. That makes sense because if you have something like log... Oh yeah, I think I already did this. Like 5 equals x. You put the hat on. 5x equals 5. And then if 5 has the invisible 1, then it's always, cross these out, x equals 1. Okay, well then I might have done things wrong. I don't know if, well, I mean, it kind of makes sense though, right? Oh. Log x to the 1 equals y. No. Oh, I know why. I think it's because wait, no, did I set this as 0? Is that why it doesn't work? Sorry, I'm getting ahead of myself. Nope. Let's try 10. Okay. Put the hat on. 10x equals 1. Yeah, no, I think this is it. I think this is a thing. Where any log with any base value, no matter what it is, if you don't have anything defined to be equal, but the inner value is 1, then I think this can be simplified to... Oh no, wait, hold on. Then this equals 0. Don't quote me on this. I could be horribly wrong, okay? To anyone that I'm going to mislead with that little equation, I'm so sorry. I got a little distracted and ahead of myself. Let me go back to the book and refer to the actual material. Oh, dang it. I'm right. And you know what? I could have figured out I was right if I just like read instead of just doing the math first. Ah, well, there you go. That's another important lesson for today. Read the whole textbook before you start doing math. Look at that. Right smack dab in the middle. No matter what you have as the base value, if you have 1, the whole thing equals 0. And if these things line up, then you have 1. Alright, so to that end, with this made-up equation that I did, where if you have 1 over 5, then you could break them apart, where you have log some variable to 1, that'd be 0. And if the bottom base value matches the number, then that becomes 1. Then you just have negative 1. Boom. Oh, okay, cool. Now this ln and the e is about natural logs, and unfortunately I ran out of time today, so I cannot cover natural logs today, but I'll do that next week for sure. And again, if anyone's working on this currently, or they have very specific math problems that they'd like me to go over, then please come by. What I would like to do is to do live tutoring on that assignment. Otherwise, if you want to do this reading on yourself or have someone providing more comprehensive explanation, I would recommend checking out this guy, Malev, M-A-L-E-V, and his series on his playlist series on log functions. He explains it very detailed and in a very well written way. And if you really want to, if it's a little too slow for you, you could put on ×2 speed and listen to it that way. That's how I did it, and it works great for me. So there's that option as well too. Okay, but next week I will cover natural logs, unless there's another request. But to anyone that came by, thank you so much for coming by to check out this lesson on logs, and I hope you have a good one. Oh, also, is there anyone in my thing? I'm learning how to raid, okay? I'm gonna try to figure out how to raid. Give me a moment. What's a... Oh, here it is. Oh, it's an actual button. Well, that's lovely. Okay. I know who to raid into. I'm going to raid into the other streamer who requested this kind of material, and this will be Trent Deadwood. He's a great guy. He does fighting content. So to anyone that's here, hey, enjoy his stuff, and I hope he enjoys his logs. Let's see. This one. Alright. I'm gonna try to beat the timer. How long do I set a raid for? Do I just press the button? Okay. Alright, enjoy. Have a good one. Oh wait, no, it's gonna be a whole minute. Okay, that's fine. But yeah, to anyone here, I'm gonna try to raid into Trent Deadwood. He's the one that requested this material. So if you want to make jabs at him about logs and how he should have been here, you could do that. That'd be cheeky.